Hi, students. How are you? And happy St. Patrick's Day. I'm going to try to draw my shamrock. There we go. So, we have a fun day of math and other things planned for today, March 17th. We'll start with our Do Now, where we have a great question today about luck. Not just luck of the Irish, but luck for everybody. Our objective is to put together what we've been working on with adding, subtracting, and multiplying monomials. Our essential question is, how do the monomial operation rules work together? So we've been doing this and we've been doing that, and now we're putting it all together. So our assignment is to complete the do now. We're going to complete the work page. We're going to complete the exit ticket, but you know that all important piece that gets you your participation. Show your work to me. And if you don't get to finish, you can finish for homework, but you still should show me what you've done in class. So we have a little silliness today. I say leprechauns work hard and play hard. If you finish early, enjoy the mindful arts and mindful game exercise that I put for you below. We'll get back to our exit ticket in a little bit, but let's talk about today. And after we talk about today, we will get to our lesson. Okay, so our do now for today talks about luck. Okay, you may not think that's a mathematical concept, but it really is, because it calls to mind ideas of things that are random or this idea of probability. So let's just have a little math fun with the idea of luck. So the first question is, do you believe in good luck? Okay, and a lot of people think that you can kind of make luck by being positive, by seeing the cup as half full. You can kind of set the tone for good things to happen. But from a math standpoint, mathematically, what does it mean to be lucky? How does that relate to probability? And can you change your luck? I do believe in mathematical laws of probability, of course, but I do think that there are ways that we can behave in certain ways to increase our probability or likelihood that things will happen. And so, if you have some ideas on that, I'd love to hear what you have to say right here. So, go ahead and spend a minute on that now. Meanwhile, we are going to add, subtract, multiply those monomials. We've been working a little bit on this. So we know, first of all, when we add and subtract monomials, we are simply combining like terms. The most important thing is to look at the monomial carefully and make sure you have like terms. And in number one, we have 7k plus 4k. So that's a little bit of an easy one. That is 11k. 7 plus 4 is 11. Now here our like terms are x squared. So we have 11x squared minus, we're subtracting, so we don't do anything with the exponents when we subtract. Those are just like terms, and we add or subtract the coefficient. Remember, the coefficient is the number in front of the letter or variable. So we just think of this as 11 minus 3, which equals 8. So that would be 8x squared. In number 3, let's check our terms and see if they are like terms. We have m squared, n squared, m squared, n squared. Yes, so we can subtract. That would be negative 2 minus 3, which is negative 5. So the answer would be negative 5 m squared, n squared. And that's a final answer. Now, number 4, in algebra, sometimes you see this where we have a plus sign in front of a negative sign. Okay, this problem could be rewritten 3p to the 5th power minus 4p to the 5th power. Both of those problems say the same thing. They're the same. Now, when we look at 3p, we have to ask, is it positive or negative? If there's no sign in front of it, that's positive. Do we have like terms? Well, we have p to the fifth power here, and we have p to the fifth power here. So they are like terms. So basically, this is 3, which is a positive 3, minus 4. Well, 3 minus 4 is negative 1. But we don't write in negative 1p or x. It's just negative p, and remember, it is p to the fifth power. And that's the final answer. So number 5, let's check for like terms. C to the seventh, D to the second, same with both of them. So this is negative 14 plus 7. Remember, ignore the sign, subtract, and keep the sign of the larger absolute value number. So that would be, if 14 is larger than 7, our answer will be a negative. 14 minus 7 is 7. So that would mean negative 7, c to the seventh power, d to the second power is our final answer. So why don't you try 6, 7, 8, 9, and we'll stop there, and then we'll talk about these ones, number 10 and 11. So take a minute and work on those. Okay, I hope you paused the video and you tried this. So number 6, we have RS, but here we're subtracting a negative. Okay, and that's when we subtract a negative, the easiest way to handle that is that's adding a positive, because you're negating the negation. You're doing the opposite. So what it ends up being is negative 10 plus 14. So 14 is larger than 10. So our answer will be positive. 10 minus 14, 14 minus 10, excuse me, is 4. So we are going to have a positive 4, and then our variable RS. Number 8, we have an A term, another A term, then we have two B terms. We'll start in ABC order. We have negative 8 plus 3. Negative 8 plus 3 is negative 5. And that's our A term. So this is done. This is done. Now our B term, we have an invisible 1 here. So it's negative 1 minus 2, which would be negative 3. So that would be negative 3b, and there's our final answer. Okay, number 8, we have x, 6x, negative x, which is negative 1x. We have an invisible 1 there. We also have negative 4x squared and positive 5x squared, and then we have this constant that's all by itself. We'll deal with that at the very end. We write these with the largest exponent first, and the constant is always at the end. So we'll start with the x squared. So we have negative 4 plus 5. So negative 4 plus 5 equals 1. So that would be 1x squared. We don't write the 1, it becomes invisible. We just write x squared, and it's understood that that's 1x squared. Now the x's, we have 6 plus 6, where's my x? Here it is, minus 1. So that's 6 minus 1 is 5, and that's a positive 5x. And then I have that negative 7, that constant, that number without a variable at the end, and that's our final answer. In number 9, I have CD, I have C squared, I have 1D squared, negative 1. I have another 4D squared and negative 11CD. So there's a lot going on. I'm going to start with the C squared terms. I have positive 2 plus, oops, that's a D, that's not a C. I have positive 2 c squared, and that's all I have for c squared. So that'll start us out. 2c squared. Done with that. So let's look at the CD terms. I have 10CD minus 11CD. So 10 minus 11 equals -1. So that's negative CD. The 1 becomes invisible, and we're done with that. And then I have -1d squared plus 4. So -1 plus 4 is 3. So that's a positive 3d squared. So I did this alphabetically with the C, then the CD term, and then the D term. Now, when it says to find the difference of, so difference is subtraction. So here we need to subtract. And of 9p3q2 and 13p3q2. So when it's written like that, we assume they want to subtract the smaller from the larger. Now also, let's check for like terms. They both have p3q2. So this is a matter of 13 minus 9, which would be 4. So the answer would be 4 of that p3 Q2. Now, number 11, we have to be really careful with this. We've got a couple of things we need to do. We need to subtract -2x squared from the sum of 4x squared plus 15x squared. So first we need to add 4x squared plus 15x squared. Well, 4 plus 15 make 19x squared. And then this is our turnaround phrase. We have to subtract the 2x from it. So we call that a turnaround phrase. So 19x squared minus 2x squared and minus a -2x squared. Let's correct this. Write this very carefully because this is tricky. So we're subtracting -2x squared, okay? And remember, when we subtract a negative, we go ahead and make it positive. So 19 plus 2 is 21x squared. All right, let's see what we're going to do with the rest of this paper. We have directions that say simplify. That means we'll evaluate the following monomials, and we're going to express the final answers using only positive exponents. And let's recall, if you have a negative exponent, like x to the -2, you need to put it under a 1 in the denominator, and you can make the exponent positive. So we've got 2 to the 9th times 2 to the 13th. We need to use the product rule. The product is the answer you get when you multiply. And the product rule says if you have x to the a times x to the b, to multiply them, you simply multipy the numbers if you need to. There's sometimes you will, sometimes you won't, but add the exponents. So this would be a plus b. So you'll add those exponents together. Let's see how this works. 2 to the 9th times 2 to the 13th is going to equal 2 to the 9 plus 13, which will equal 2 to the 22nd, excuse me. 13 and 9 is 22. Be careful when you write your exponents. Okay, moving on. 8 times 8 to the -5th. We have to add, this has an invisible exponent of 1, so it would be 1 minus 5. Okay, so 1 minus 5 is going to be -4. So it will be 8 to the -4th power, but we were asked to only write positive exponents. So we have to drop that in the denominator under 1, and this exponent now becomes positive. And our answer is 1 over 8 to the 4th power. If you were to evaluate this on a calculator, it would be 1 over 4,096. Big number. Number 14, negative 10 to the 6th power times negative 10 to the negative 6th power. Well, that would be negative 10 to the 6 minus 6 power. So negative 10 to the 0 power. Anything raised to a 0 power equals 1. So don't forget that rule. So number 15, we have a to the 4th times a to the 2nd. So that would be a to the 4 plus 2, which would be a to the 6th power. Number 16, we have k to the 3rd times k to the negative 8. That would be k to the 3 minus 8, which would be k to the negative 5 power. We don't want negative exponents, so we drop it into the denominator under a 1 and make the exponent positive. So number 17, we have x to the 8th power times x to the negative 1 power. So that would be x to the 8 minus 1, which would equal x to the 7th power. So try some of these on your own. Pause the video and let's see how you do on your own. Okay, number 18. We have w times w times w, w to the 5th, negative 7th, and then we have that invisible 1. So we have to add 5 minus 7 plus 1. 5 minus 7 is negative 2, plus 1 is negative 1. So that would be w to the negative 1st power, which we drop that into the denominator. We have now w to the 1st power, but that can become an invisible 1. So 1 over w is our final answer. Number 19, we have c to the negative 5th times d to the negative 1st times c to the positive 4. Negative 5 minus 1 is negative 6. And negative 6, oh, I'm sorry, I mixed up my C's and D's. I think I need to make this a little bigger so I can see it better. Let's start that again. We have c to the negative 5th and c to the 4th. So on the c's, it's negative 5 plus 4, which would equal c to the negative power of negative 1. So we have c to the negative 1st power. And then this d does not need to combine with anything, so we just write it down, d to the negative 1 power. Well, they both have negative exponents, so we're going to drop them both into the denominator. They now have an exponent of 1, but the exponent of 1 becomes invisible. So number 20, we have p to the negative 2, q to the negative 1, p to the 11, and q to the negative 6. So first let's do our p's, then our q's. Negative 2 plus 11 is 9. So that would be p to the 9th power. Now q, we have negative 1 minus 6. So negative 1 minus 6 is negative 7. So that would be q to the negative 7th power. So we don't want a negative exponent, so we'll put that under p to the 9th in the numerator, but the q goes in the denominator with an exponent of 7. So that's how that looks when you finish simplifying. So number 21. So remember, with these, first you multiply the coefficient, and then you use the product rule on the exponents. So 7 times 5 is 35. X, 4 plus 3 is 7. And 35x to the 7th is our final answer. So number 22, 9 times negative 2 is negative 18. K to the 5th times k to the negative second. We add 5 minus 2, which would give us k to the third power. Number 23, negative 4 times negative 3 is a positive 12. And for the variable, we have v to the third, and we have v to the negative 10th. That would be v3 minus 10 would be negative 7. So it looks like we're going to have to put that in the denominator so we can make the exponent positive. So the numerator will be 12, and the denominator will be v to the 7th power. All right, number 25. 2xy times 5, x to the 8th, y to the 3rd. So 2 times 5 is 10, and x, we have an invisible 1. 1 plus 8 is 9. And then our y's, we have 1 plus 3 is 4. And that's a final answer because we don't have any negative exponents to drop into the denominator. So number 25, we're multiplying 2/3 times negative 18. Okay, so I think maybe we need more room to do this. So let's write this out. We have 2/3, that's a positive 3, okay. A to the negative 2 power, b to the negative 1 power, times a negative 18, boy, throwing a lot at us, a to the negative 3rd power, b to the 1st power. So let's start with 2/3 times negative 18. So we have 2/3 times negative 18, and we can drop a 1 under there. Now we can simplify this using the rules we used earlier in the year. 3 divided by 3 is 1, and 18 divided by 3 is 6. So 6 times 2 is 12, and that's a positive times a negative. So that's a negative 12. Negative 12 under 1, which is negative 12. So we have negative 12. Now we have a to the negative 2nd power times a to the negative 3rd. And we have to add those exponents. So negative 2 minus 3 is negative 5. So that would be a to the negative 5th power. And b, in the b terms, we have negative 1 plus 1, which would be b to the 0 power. Couple of things to keep in mind here. So first of all, this b to the 0 power will equal 1. So 12 can stay in the numerator, but the a to the negative 5th has to go in the denominator. So let's put this all together. We'll have negative 12 in the numerator, a to the 5th. Now the exponent is positive now because we put it in the denominator. And b to the 0 power equals 1. So it goes away. We don't have to put that anywhere. So that's our final answer. So let's write that down. That would be negative 12 in the numerator, and that would be a to the 5th in the denominator, and that's our final answer. Okay, number 26. We have negative 4 m to the 5th n to the 7th. We have mn, and these are both invisible exponents of 1. And we have negative 2 m to the 2nd n to the 6th, and we are multiplying everything. So we start out with, we have an invisible 1 here, we have a 2 there. So negative 4 times 1 is negative 4, and negative 4 times negative 2 is a positive 8. So negative times a negative is a positive. Now let's do the m terms. We have 5, we're adding the exponents, and 1 makes 6, and 2 more make 8. Now we'll do the end terms. We have 7 plus this invisible 1, that makes 8, and 6 more makes 14. And that's our final answer. 8m to the 8th n to the 14th power. And then number 27. So what do we got? We have a, b, c to the third. Now remember, a and b have exponents of 1. We have a to the 6th, b to the 4th, so we're multiplying these, and then we're adding 9, a to the 7th, b to the 5th, c to the 3rd. So watch how this works. First, we do the multiplication. Multiplication and division always before addition and subtraction. So we'll start with a. We have 1 plus 6 is 7. B, 1 plus 4 is 5. And then C to the third. Okay, and that finishes everything up there. Plus this amount here, the 9, A to the 7th, B to the 5th, C to the 3rd. Now I hope you noticed that we now have like terms. A to the 7th, B to the 5th, C to the 3rd in both of those terms. And that's what we need when we add. We have to have like terms. Now, first of all, we have an invisible 1 in front of this. So this would be 1 plus 9 equals 10. And the term is A to the 7th, B to the 5th, C to the 3rd, and that is complete. And now, number 28, our last problem today. We have multiplication here, we have multiplication here, and subtraction in the middle. So the subtraction we're going to do last. So we have 10 times 2 is 20, and then we have our h, 10 minus 1 is 9. And then from that, we're going to subtract 3. We got an invisible 1 here. 3 times 1 is 1. So that would be 3. H, 5 plus 4 is 9. And again, we've got like terms that we can work with. We have h to the 9th power. So now what we have here is 20 minus 3, and that would be 17 h to the 9th power. So good job. Let's go back to our exit ticket and let's really rock and roll this thing. So what should you do with a negative exponent? Well, let's change our color and put something that shows up. Place the term with a negative exponent in the denominator and then make the exponent positive. Okay, so I don't know if you noticed that today I have something a little extra for you. Some of you do finish a little bit early. And if you don't finish early, that's fine. I mean, you could do this later. But, since we're talking about St. Patrick's Day and being lucky and lucky charms and different things, I guess we don't really believe in luck. But, sometimes having a little charm can just be a reminder. You can always have a symbol or a tradition or something, just something that keeps you positive. Some people have a lucky penny, or maybe you have a picture of someone that helps you stay positive and stay focused and get your schoolwork done. So I just thought it would be really fun to design your own good luck charm. Maybe I'm going to design a lucky 4-leaf clover for my good luck charm. I hope you can draw better than me. And maybe I'm going to surround it with a heart. Okay, maybe that's my good luck charm. Just having a little bit of fun here. I'll color it in a little bit. So there's my lucky charm. Design something for yourself. You could design a horseshoe or a flower, anything that just makes you happy. And then we have some hidden picture fun, and I think when you click on that, you're going to have a few minutes of fun. So, and that's what it's all about. We work hard, but we also like to have fun. I appreciate all your hard work. I appreciate you finishing your lesson, and I appreciate how you show me your work. So listen, remember, it takes lots of practice, but you know, as always, if you practice, you'll be great.